Okay, now it works well.
Now it works well. Great. Okay. Perfect. So yeah, so again, thank you for the invitation. So the topic that we are going to discuss today is the topic of text representation. As I've seen already from a bit from the other teachers that are giving lessons on this summer school, I see that the focus is a lot on NLP and text, like how to deal with text in your daily research or on the things that you're doing. So the things that I prepared for you are in line with the things that you are discussing in these days. And I've seen also that other teachers are also discussing some things that are very similar to the things that I'm going to discuss with you today. So the topics that we're going to discuss are mostly how to deal with how to train machine learning models to do, for example, text classification. But before you give text to a computer to make a task such as text classification, you have to decide how you represent your text in order to give this information to the machinery that you are going to train. Okay, so the topics, the things that I prepared for you today are things related to how you represent your source of information, how you present text to train a good machine learning model. And we are going to discuss mainly three different ways that you represent text. There is the classical, let's say, way to represent text. That is the bag of words way, and I think that you already have some information about this. I don't know if you can. I know it's difficult by distance to have some interaction, but if you can answer me, I don't know if there is anybody that can say yes, no, maybe. So that would be nice also to have a sort of conversation if it is by distance. I don't know if you already had some lessons that about the topic of text classification, right? The last days, I think, or today or yesterday, I think. I don't know, maybe Michael, if you can also, if you're around.
I will stay here and be the interpreter.
Okay. Because it's quite difficult to I don't know if I'm still connected, if you're listening. It's quite difficult it's quite difficult to make it by distance, but I hope that since there is a lot of practical things that we're going to do, so if you can make it more interactive, it will be better. So just let me know if there is any problem. I don't know if you can listen me, if it's a bit difficult to understand or something like that. So just let me know. So I was talking about the three different ways of text representation that we are going to see in this lesson. The first is the bag of words, classical bag of words representation. And this is, I would say, a more, since it is a very classical way of doing machine learning on text, it's not, let's say, it's an easy exercise, I would say. So we start with something that is more easy. Then I think that you already have seen in the last lessons word embeddings. So that's a second different way of representing words, text. Every word represents as a vector in some multi-dimensional space. And we are going to see some problems with word embeddings, why word embeddings sometimes does not work. And then you are going to go for, we are going to a very, let's say, an exercise that is, let's say, that use some of the models that are very complex, the less models that have been used in literature and also by companies to do things like text classification and dealing with text. So it's, let's say, a very advanced exercise. So a very simple exercise that we're going to do, let's say, middle difficulty exercise with word embeddings, and one that is very advanced exercise. So if you don't follow exactly let's say, the last part, you can go, let's say, I'll give you some pointers also to go on the literature to find more about it. Okay, so the exercise are available on GitHub. So the Git page, probably you already know, is this page here. The exercises are these. So there is one notebook that is just with the setup of the environment. Then there is the second exercise that is the bag of words. A third exercise that where we are dealing with text classification, but using Word2Vec, so word embeddings. And the third one, we are going to use transformers. It's a very advanced model for text classification and also for translation. So I put here also an example of translation using transformers that might be useful if you are going to if you are going to need some type of translation during the projects that you are going to make. Okay, so these are the exercise, the notebooks. I think that you probably already know how to check out the repository and maybe open the notebooks. I don't know if how we can deal with this step. But I can, at least the first part, I can try to follow with you to see if everything works also for you. So the first thing that you have to do is so all the steps to set up the environment are both here on the README, but also here in this notebook here. So you can also open on GitHub and you see the content of the notebook. So first you check out the repository, and then you go to the folder of your repository. Okay, so let me see if I can do some of these steps with you. Okay, so the first thing, you have to check out everything. So let's go to the exercise and do a git checkout, git clone of this repo. Okay, and then you're going to download everything that is needed for the exercise and everything that is available on that repository. Okay.
Now.
Yeah, I know. I already downloaded it, so I'm just like following the steps, just so you know how to proceed. Once you do a checkout of the repository, then you go to the folder. So CD to the folder where you have this project. And then probably you should have already Conda installed, right, Michele? I don't know if everybody has already Conda installed, or I have to say also that everything that is in this repository, you can either use Conda for it with the Jupyter Notebook, or you can use also the Colab environment, Google Colab environment. And in just a minute, I'll give you the pointers on how to do it also on the Google Colab. So you just check that you have Conda installed with this Conda ---- version. And then you have to install the environment using this conda create env create conda env create -f environment.iml. And everything, all the libraries that are needed for these notebooks are there. So this line here should install everything for you. Okay. With this, we're going to install an environment that is called transformers. Okay. So to activate this environment, you have just to call this other line, conda activate transformers, and then you're ready, and you can open your and then you are going to activate the libraries that were installed in this environment. And this line here is just so you install, so you can see also on the Jupyter notebook that you already have installed. You can also see there this environment here. Okay. Okay. So, okay. I did check out the GitHub repository. So now I go to this environment, CD, so Panisson, text representation learning. In this same folder, you should have this environment.yml. So now you go there and you do this conda env create -f environment.yml. Okay. You do that, you should install everything. I already have everything installed. So conda activate transformers. And then you should see this path here, the transformers in your path. And then you do the install of the kernel on Jupyter Notebook. Okay, and you should be, everything should be installed at this point for you. Okay. So these are the steps to set up everything. It is going to take some time, I know, for everybody, because it's going to download libraries and it takes some time to also. So after you do that, you can open. So if you go here now, Jupyter Notebook. And it should open in a browser the notebooks that you see there. Okay. You open the environment setup. This runs just if you are running on Colab. And is to import.
André, can you increase the zoom a little bit of the...
Sure, yes. Thank you.
Thanks.
Thank you for the feedback. If everything is okay, if everything is installed, this second line should run without errors. Okay. This is just a line to download a database. So you'll see the database that you're going to use in the next exercise are these IMDb database. So just in the meantime, while you are also installed and if everything runs, you can also download this database in the meantime. And you can see what is the first text, the first thing that you have in this database.
There is a question.
Yes.
So in case we install that locally with conda activate you just described, and we would not, so is there any requirements with respect to a graphic card, and would it work also without graphic card, or what's your experience there?
Yes, it should all work without any graphics card. It should install locally without any problem. Okay. There are libraries there like PyTorch that are libraries for deep learning, but they don't need any graphical cards on it. Okay. The only problem with running it locally is that the last exercise is going to be very slow. So for that last exercise, since I'm running locally, I'm also going to run on Google Colab. Okay. So I'll just show you also how to, so I'll take this chance also and your question, thank you, for showing how to run this everything on Colab also. So if you go back to the main page of this my list of this exercise, you'll see at the end of the page, you'll see this like if everything doesn't work, if the setup doesn't work, or if you are still waiting for the setup, if you are still waiting for installing the libraries, you still should be able to open the notebooks on Google Colab. So if you just click here, you'll see that it's going to open a page on Google Colab, and the same notebook that I opened here, just with different colors. You see that you have just a warning because it's not authored by Google. I'm not Google, so you can run anyway. So you can run this cell here. This cell is going to install everything that is needed for this exercise, this notebook at least. Okay. You see these lines of libraries being installed. Okay. And don't worry if you see a warning like this error at the end. Like this error at the end happens. I don't know exactly why, but everything works even if we have this error here. Okay. Then you see that the import works. Then it downloads the database. It takes just a few seconds. And then you can print the first, after it downloads, you can print the first entry of this database. Just give it a few seconds. In the meantime, if you have any words, I don't know if you can give me some feedback if people are having any problems or if everything is working.
We are actually trying to do this now.
Many are trying. But yeah, of course, if there are questions, let us know.
Okay. How's it going? Everything good?
Yeah, seems so. Okay.
So I'll go forward. So this notebook should work in Colab. If you install all the libraries also locally, it should work also locally. So I'll go back just to our GitHub. Then we have the three exercises here: the bag of words, word to bag, transformers, with two parts. One that is the training part, and the second one is the testing part. Okay. Just before we go forward with and while I don't know, probably some people are just waiting for the installation, we're waiting for downloading a data set or something like that. So in the meantime, so we already spent something like 15 minutes on the lesson. So while you are waiting, while you are following these lines here, these common lines to set up the environment, I'll just give you some words. I have a couple of slides just to explain a bit more about what is text representation and about something more about the three different types of text representation that we are going to use today. Okay. So let me just activate Keynote. Okay. Can you see it?
Yeah.
Okay, can you see the presentation?
Yeah, very well.
Okay, good. So while you are installing everything, it takes time. I'm going to talk a bit, okay? So text representation learning. First thing, what is text representation learning? So it's one of the main steps of building machine learning models for text analysis, NLP, text classification, translation, everything that deals with text needs to pass through a first step that is text representation. You have to decide how you present text in order to give it as input to your machine learning model task. So here, as an example, I'm showing how a text classification task, but the text representation part is before this before you train your machine learning model. So is this some people also call it feature extraction. So you take your data set, you take your text, your documents, and for every document you have to decide how you extract features or how you represent your data in some way that is using numbers. So document is, as you know, a document is normally is represented as a string, and a data set of documents will be a list of strings. Okay, so you have to decide how to represent these strings as numbers, because machine learning models, they understand numbers. Okay, so the three main approaches that we're going to see: bag of words, word embeddings, and also contextual word embeddings. Okay. The bag of words approach is the classical one. So in this case, each word is represented as a binary vector with d positions. So it's a very long vector, and the size of this vector is the same size of the vocabulary. So if you have a vocabulary of 1,000,000 words, your word will be represented as a binary vector with one set only on the index that represents that word. Okay, and the way that a document is represented in the bag of words approach is just as the sum of the word vectors. So you take all these word vectors, you sum all these vectors, and you'll see a sort of count vector. You see that, for example, a document that is the cat set is going to be 1 to the, 1 to cat, and 1 to set, and zeros everywhere. And the other, in all other words that you have in your vocabulary are going to be zeros. Okay. There are 3 examples here, just so you have. Since you are summing over all the words in the document, so it works like a sort of counter of words in the document. Okay. So it's a quite straightforward way of representing a document. It's very popular way, and it works most of the time. Okay. But there are some problems with this type of representation. Okay, so the first one is that the vocabulary or the dictionary that you were using to represent all the words, it might be huge. So you might have, for example, in a very big corpus, you might have 1,000,000 of different words in your vocabulary. So this dictionary is going to be very huge. So a machine learning model needs to learn millions of parameters if you are going to train a classical one, like, for example, support vector machine or another one. We are going to see an example in the exercise. Okay. Also, another problem is that each word is completely the representation of each word is completely independent of each other. For example, if you look at the representation of the word amazing and the word awesome, they are very similar semantically, but they are not similar in terms of vectors in representation. Their representations are not similar. They are as distant as the words amazing and terrible. Okay. So this is a problem with the bag of words approach. You cannot represent semantics with this approach. Okay. Okay, so then let's go to the next. There's any question about this approach?
No, it seems not.
Okay. Next, word embeddings. So with word embeddings, in this case, each word is represented as a vector with d real numbers, where d is a number that is much smaller than dictionary size. Typically, I don't know, 100, 500, at most 1,000. Okay, but it's much smaller than a million, as you will have in the case of the bag of words approach. Okay, so each word is represented as a vector. It's not a binary vector; it's a vector of real numbers. Okay, and D is called also called the dimensionality of the representation. So it's let's say it's a vector in D dimensions. Okay, and you can see here in this example, it's like vectors with 4 dimensions. Like king is represented as 4 different values. Man is represented as another 4 different values, and woman is another another vector with 4 different values. And you can see that words that are semantically similar, they are also similar in terms of these numbers. So for example, man is more similar to woman than woman is similar to king. Okay, you can see by the colors more or less. I tried to represent through the colors, but I think that you can more or less see these, let's say, similarity between different words. So a nice thing with word embeddings is that these, let's say, these are vector representation. With this vector representation, you also can represent semantically these words. Okay. Any question? I think that you have already seen in the past lessons something about this.
Yeah.
Okay, good. So what are the problems with okay, first thing, the most popular implementation probably already have seen is word2vec, where the vectors are obtained. So there is a neural network that is trained on the task of predicting a word. You take the neighbors of that word, you show the neighbors to the machine learning model, and the machine learning model has to predict what are the words that was associated to that word neighbors. Okay. So it's very popular also for translation tasks because a word in one language can be also represented semantically in the same way in another language. So yeah, it's just numbers. You don't have a language in the middle. So you can easily translate. If you have the same representation in different languages, you can easily translate from one language to the other, even if the translation is not exact. Like, for example, if you take these 2 words, amazing or awesome, in English, they are exactly the same. They probably have very similar representations in word embeddings. And in another language, if you take the vector that is more similar to the vectors of these words in English, then you have a good translation of that word. Okay. Also, a problem with word representation, with representing words in this way, is that they are independent of their context. For example, I give you here an example. The representation of apple, the fruit, has exactly the same vector representation as the word vector, but the company. Because you have this dictionary mapping. You cannot have, for the same key, you cannot have 2 different representations, okay? For one key, for one word, you have one and only one representation for that word, okay? That's clear? Any question?
No.
No. Okay, and the last one that you are going to see, we are not going to see the details of these models, but the goal of these, since we don't have much time, is just right now we just have if you give me the 90 minutes, I think we have 1 hour at least. So we are going to just use it. I can give you pointers on how to learn more about these very complex models. But let's say the most popular example of these models are the transformers. The interesting thing about these models is that they are contextual word embeddings. It means that they are able to, if you give a text, they are able for each word give you a vector representation for that word, but the vector representation that you have for that word depends also on the context. So in this case, the representation for apple fruit will be different from the representation of apple company. Okay? Any question?
Yeah.
Okay, so let's go back to the exercise. Okay. So we have, we still have an hour, more or less. Okay, I think I have sufficient battery. I was very quick on moving because this difference in an hour, I was very quick to move my computer. But if I need to run to get my my charger, I'll ask a minute for you just for that. Sorry about that. Okay, so let's go back to the exercises. So let's start with the notebook with the bag of words. Okay, so if you go to the Jupyter notebook, I don't know there is anybody in the audience that was already able to open this notebook and see the same things that I'm seeing here. Just to know how many are following with their notebooks, how many are following maybe with Google Colab, or
yeah, a few hands up. Someone opened the notebooks. Yeah.
Okay, great. Okay. If if you are not able to install everything, just click on the link and open on Google Colab. Okay. So let's open this notebook. Okay. So first thing, we just open I'm sorry. I don't need it right now. Okay. Okay. Any of you had some problem as me? I don't know, was not able to import things. I don't know if there is how many people are following. I updated yesterday the environment and I added also matplotlib. So I hope that for the people that are following and try to run it on locally, they are able also to run without comment this line. I don't know. Just to, so I don't know how many are running locally. If anybody has a problem here, or who's running locally, if didn't have any problem. I don't know. Any feedback?
Yeah, I think it's fine.
It's fine. It's running. Okay. Yeah, the environment that I updated yesterday should be okay. Should include also matplotlib. Okay. So first one, the traditional approach to text classification. We are going to see the bag of words representation. First thing, let's see the data set that we are going to play with in this notebook. Okay. The data set is called IMDb. IMDb stands for Internet Movie Database. So if you open the IMDb, if you search for it on Google also and open the first link, you'll see that the site imdb.com is let's say the biggest website with all the catalogs and databases, with all the movies that have already been out. Say. The interesting thing on this site is that you have all the information about the movies with actors and a lot of things, but also there are a lot of reviews about the movies. So the exercise that we are going to do is using these reviews. The reviews can be positive or negative. So this exercise works like a sort of sentiment analysis. So if a review is positive, it's like a positive sentiment. If a review is negative, it's like a negative sentiment. So, okay. So it's a text classification. It's a database, a data set for text classification, where you can use these the sentiment, positive or negative, as the class of the and the label of the review. Okay. So let's see. So the first thing, you just run this cell here, and you should be able to download the data set. If you download it one time, then it should be already in cache. And this is the thing that you see here. Since I already downloaded the data set locally, I just see this line here saying that I'm reusing the data set that they already downloaded. Okay. Okay, so we are going to, this data set has a lot of reviews, like 25,000 different reviews, but we are going to use just 5,000 because we don't want to stay here until tomorrow waiting for our models to train. Okay, so just so we can just make a quick exercise with this data set, we are going to use just 5,000 examples. Okay, 5,000 for training and also 5,000 for test. Okay, so we just assign for different variables the training documents, the train target, the test documents, and the test target. And you can see, like, for example, the training document with index 10. Okay, and you see that this is the review number 10. If you look, if you read carefully this review, you see that it's a very negative review. Okay. And you see that the target, like a train target, is of the index 10 is 0. It means that 0 is a negative review, 1 is a positive review. Okay. Okay. With this line, this line is just to show you how many positives and how many negatives there are in this data set. So around 2.5 thousand for each class. Okay.
Yeah.
Any question up to here?
No, seems good.
Okay, great. So let's go to the interesting part for processing of the text using the bag of words approach. Okay. For the bag of words approach, for quickly running this exercise, we are going to use many classes from the library scikit-learn. So the main class that does this bag of words representation is this count vectorizer. It's like just creates for every document a vector of counts of words. Okay. Then we are going to do some transformation, and we're going to see why we do this transformation. The machine learning models that we are going to use is these. We are going to use, I've put here this class here, but you can use a different machine learning model also. I think we're going to use a different also later model. Let me see. Yes, yeah, we're going to use, sorry, logistic regression. It's not this model that we're going to use. This is not valid. Okay, forget about multinomial net base. Okay. Then we are going to validate with using cross-validation and evaluate using confusion matrix and accuracy score. But you'll see later how we do these steps. First, let's see how we use the count vectorizer. So we just create an object with this class count vectorizer. We call fit transform in the training documents. Okay. Okay, let me just run. Oh, Okay, this also was also updated yesterday, so I'll run this in Colab. Sorry about it. Okay. Give me just a second. It's not going to run also in Colab. Oops. Yeah, I'll need just a second just to update my environment with scikit-learn. Sorry about that. I thought I will have the time to update the environment, but I didn't have that time. Okay. So now it should work. Okay, once we import all the libraries, then okay, then we create this count vectorizer. We fit this object using the training documents that we have. So this fit transform is going to create the dictionary of words and also create all the representation using bag of words for each one of these documents that you have in the training dataset. Okay, and then I'm just assigning in this variable here that I called feature names all the words that are in this vocabulary. I'll just show you I'll show in just a minute. So you just call it. It should be very quick to fit. And you'll see that in the feature names, you have, you see the dictionary of all the words. Let's see the first 100. You see that since it's sorted in alphabetical order, all the first ones are numbers. Okay, if you go from, let's say, 1000 to 1100, you'll see that these all words that start with A. Okay. It's sorted in alphabetical order, and you can see also what's the size of this dictionary. And we have a dictionary of 38,000 words, okay? So if you look at this C, so this is the result of the bag of words approach, C. It's a matrix with 5,000 rows and 38,000 columns. So for every column in this matrix, you have a counter for each one of the 5,000 documents that we have in our data set. Okay, so this is the representation using bag of words, and you'll see that here in this line, I'm just showing you for each word in the dictionary. For the document number 10, that is the one that you have seen here, the very bad review, very bad review. What's the count of each word in this review? Okay, and you can see that the most common word is the word "the," is an article. Okay, that's okay. Then you have film, is, and, of, all very common words. As you can imagine, these are not the most important words in this document. Probably the most important words are, if you look at the review, there are some words, let's say, script so banal and things like that. So there are other words that can tell you that this review is bad, and not articles, probably. Okay. So the first thing that we are going to do with the result of this bag of words counting approach is to apply TF-IDF weighting. TF-IDF means just term frequency divided by document frequency. Okay, so what we are going to do is just take the frequency here, take this number here, and divide by the log of the number of times that this word appears in all the documents in the data set. So the more common is the word, the bigger is the denominator of this number. Okay, because the more documents this word appears. Okay, with this weighting, then you see that more interesting. There are more interesting things that appear. So the more important things here are not the common words that are here at the end with very low weight, but are words like ashamed, tracklist, names of actors, banal is here with a much higher weight, and things like that. So it's very useful to apply TF-IDF weighting because it gives you more weight to words that are more important in the document. Okay?
Yeah.
Okay, any question here?
Seems good.
Seems good. Okay. So let's go for the training part. And this part probably you have done in other lessons, or you are going to do in other lessons. So we are going to just quickly go through this step here. So the model that we are using in this exercise is the logistic regression model, where we model the output, let's say zeros and ones, that are the labels of the documents, as the output of this function here. So it's a bias plus the sum of a coefficient for each column of our feature matrix. Okay. So you can imagine that the bigger is the number of words that you have in the vocabulary, the higher is the number of coefficients that you need here. Okay. And this is one of the problems that I was mentioning on using the bag of words approach. Okay. So we are using this logistic regression model. Just one thing more, it's a bit more complex than just a logistic regression because we are going to add also a regularization. So it's not just this function here. We are going to use this function plus a regularization term, so we don't overfit to the training set. We are able to control how much we overfit to the training set. The way that, so we will have to choose a value, a C value among different values. I put a list here, but if you want to try other different values, I'm trying 0.1, 1, and 5. And let's see, using cross-validation, what is the performance using every different value of C. So we create our logistic regression model. We assign the hyperparameter C to this model, and we evaluate this model using cross-validation. Okay. And let's see if it works. So you'll see, oh, sorry, I have still to define this part here. No, I didn't run yet this part here. Okay. So training, let's train the model. So you see that the accuracy of using a logistic regression model with this hyperparameter C equals 5 is already very, very high, like 86% of the time that you are predicting something that you didn't see yet, we are going to predict the right class. Okay. So we This is the model selection part. We select the hyperparameter C that is better for this data set. We set C and create a new model and fit using the whole data set. Okay. Any question up to here?
No.
Okay. Then the last thing that you will do is just taking our training or testing data set. Sorry, so up to here we used just the training data set. Now we are going to get the testing data set and test if this model, how good is this model for the test data that you selected. So we have to take, so you have to apply the same transformations that we did for the training set. You have to apply also for the test. So remember that here we had this object that is the count vectorizer that we fitted using the training data. And now you are going to use this same object and just transforming the test documents using the same object. And the result is going to be this bag of words representation for the test documents, okay? And we are going also to apply the TF-IDF transformation to it. Okay, these two lines do that, okay? In the true labels, we're going to have the test target, and the predicted labels, we are going to ask the model to predict the labels for the test set, okay? So you'll see that in the true labels, now, you have the labels that are true. Let's say if they are, every document, if it is a positive or negative review. And then you have the predictions, red labels. Let's see what we have, the first prediction, first 10 predictions. And you see that sometimes it does right, sometimes it does wrong, but you can calculate how good is the model using these, how good is this model for this task here, okay? So first thing, we are going to take these true labels and also the predicted labels and build a confusion matrix. So you just call the confusion matrix from scikit-learn. As a result, you have here, this is a nicer representation with a heat map. So you see that here that you have on the diagonal, you have the true positives, so actual value true, and how the model predicted. These are the true positives. So these are samples where in the test set they were true, they are positive reviews, and in the model predicted as a positive review. Okay. These are the negative, true negatives. So in this case, it was a bad review, and the model predicted as a bad review. And in the off diagonal, you have how many examples you predicted. So in this case, it was a bad review, and the model predicted as a good review. In this case, 310. They were good reviews, but the model predicted as a bad reviews. And the accuracy is 0.88. So 88% of the time, we predicted the right class. Okay?
Yep.
Okay, good. So if everything is okay for this exercise, if you don't have any questions, I don't know, maybe we can, since I'm 6% of I'm with 6% of battery, if you give me just
take your charger.
a minute, yeah, to take my charger, and you can think about questions that you want to ask about this exercise. Okay.
Okay. Yeah.
Okay, thank you. Sorry about that. Back in a minute.
Yes. Yes, yes. So I know that they are available. Like, but not everyone might have certain on the so that was the best for people. Everyone might yeah, GPU, it might not work. Everyone has a GPU, right?
Okay.
Okay, I'm back. Questions?
I think there are no questions. One question.
Okay.
Please.
Hello. How do we decide on the number of the maximum iterations? I saw 200 you used, but how do we decide on the number of the maximum iterations?
Yeah, this is, you can put as many as you can. I just put, because the default is 100. But with the hyperparameters that I said here, 100 is not sufficient. If you just put like the default one, you'll see a lot of warnings. I think you should see, not, yeah, maybe not in this, not right now. But sometimes you might see warnings that the defeating phase arrived at the maximum number of iterations. So you, in that case, you just increase the number of iterations, and that's it. Okay, but it's not is not something that is going to impact in the performance of the model.
Okay, if it doesn't convert or may find a solution, I can raise the number of maximum.
Yes, exactly.
Okay.
Okay, great. Yeah, thanks.
Okay. More questions?
No.
Okay, if not, so let's go to the next exercise. We still have half an hour, right?
Yeah.
Okay, great. Okay, so next exercise, word2vec. So let me see if it works. Okay, so you can open locally, or you can also run on GitLab. Should be fine. This is going to install the library that we need. I hope that I have it. Sorry, just give me a second. So if you don't have, okay, perfect, okay. You should have already this library if you follow the steps for the setting up the environment. It should be installed also, Jensen. Okay. Okay. So okay, this is again the same data set as before. Okay, 5,000 samples. Okay, for training, 5,000 also for test. We assign to the same names of variables that we had before. But now we are going to do some a very similar exercise using word embeddings. Okay. So word embeddings, as I've already told you, is a way of representing text where every word in the vocabulary is represented as a vector of real numbers. Okay. I've just put here some more information about how Word2Vec, how word embeddings work. The implementation of word embeddings that we are going to use is this Word2Vec, and we are going to use a pre-trained model. So somebody already downloaded a big data set, that is this data set with a lot of Wikipedia articles, and this GigaWord data set with 6 billion words on it. It has a vocabulary of 400,000 words. And you'll see how these words are represented. Okay, so if you just first, if you import the Word2Vec model and this downloader API, when you run this step here, it should download the entire model, the training model, okay? Don't worry about the warnings, it's okay. Okay, so this object here, we assigned the result for this W2V, Word2Vec object. So it's a list of 500,000 words that are mapped to 400,000 vectors, okay? Just to see you how it works, so for example, the Word2Vec representation of the word amazing is this one. It's a vector of numbers. A vector of, and you can also check how many numbers are there. So if I do len of this vector, you see that it's a vector of 100 values, okay? So this is the representation of this word amazing in Word2Vec. If I take a different word, awesome, it's a different representation. You see that the numbers are different. But I can ask how much similar is the word amazing to the word awesome. And you'll see that the similarity in this case is 0.8, okay? If I ask how much similar the word amazing is to the word terrible, it's less similar as expected, okay? So you see that you can represent more than, let's say, you can represent the semantics of the words also using this sort of representation, okay? And you can do, so for example, if I take the top 10 words that are most similar to the word amazing, these are the top 10. So incredible, fantastic, wonderful, astonishing, marvelous, okay? And you see that the most similar one is incredible, 0.9 of similarity, okay? If you take a different word, any other word of the dictionary, like for example, I'm taking Italy, it's the name of a country. If you take the top 10 words more similar, you see that as results, you have also names of countries, okay? So semantically, they are similar, okay? If I take, just to give you an example, the word apple, and you take the top 10 most similar words, you see that the most similar ones are Microsoft, IBM, Intel, Software, Dell, and so on. So this is the representation, most probably the representation for Apple as company, not as fruit, okay? If I want to work in a text where Apple appear as the meaning of a fruit, I'm going to have problems with this representation, okay?
So Andre, I have a question here. The point is that so this is a model that was pre-trained on Wikipedia, you mean?
Yes.
Or,
yes.
So the model
Wikipedia,
trained on Wikipedia considers Apple as a company.
As a company. Yes, exactly. So it depends. You see, exactly. That's a good question because the representation really depends on the data set that they are using to train. Okay. So in this case, since it was trained on Wikipedia, there are many references on Wikipedia of Apple as company. So probably it learned that Apple, the semantics of the word Apple is a company.
Okay.
Great. More questions?
No.
Hello. Yeah, I have one question that is out of curiosity. Yeah.
Yes.
So actually, we used to measure word similarity sometime with Levenshtein distances. So how different is word-to-vec similarity with Levenshtein distance?
So if I remember well, the similarity here is measured as a cosine distance.
Yeah.
So it's a different type of measure. So if you look at definition of cosine, it's the angle of the two vectors. The Levenshtein distance is different. Has a very different definition. So yeah, they are different. I don't know. I have to say I don't know what will be the results of using Levenshtein using.
Yeah. I was interested to know that. What could be the result if I use both the things, and how far my result would be.
Yeah.
Anyway,
thank
you. Yeah. Thank you. Thank you so much.
No problem. Thank you. The interesting thing is that you can do with this sort of representation, and also that you can apply mathematical operations using different vectors. So for example, this is a classical example of if you take the representation of the word king, you remove the semantic representation of the word man, and you add the representation of woman, the result is queen. Okay. So you can play using mathematical operations. You can play with the semantics of the words. Okay, that's a very nice property of this type of representation. Okay, more questions?
No.
Okay, so let's try to build a model that does text classification using word2vec. Okay. So the problem here is that using word2vec, you have a representation for every word. But for doing text classification, you need to have a representation for every document, and not for every word. Okay. So one of the common ways of using word2vec representations for document classification is aggregating these representations in some way. For example, in using a weighted average or an average or weighted average, if you have, for example, if you can calculate the importance of each word in the data set, then you can use this importance as a weight for building this document representation. This is not exactly, but is let's say the intuition that is behind it is another approach that is doc2vec. Okay, so doc2vec is just you take a document and now you produce a vector representation for the whole document. Okay, there is an implementation of doc2vec in Jensen also, and we are going to use it. So you just import the different classes. The documents just need to be tokenized and tagged just to run this type of approach. So if you look now at these target documents, if I can select it. Target documents, so let's see the first one. So you see that it's now it's a list of words, okay? And now we are going to train a doc2vec model using these target documents, okay? You can save it on disk using this model save. So let's train this model. It should take a few seconds to train. So a few things. The biggest is the vector size. The more time you need to train this model, this representation, and also the highest is the number of epochs. The more time you need to train everything. Okay. So you trained. We save it to disk, and now let's see what is the representation of the document, the first document. Okay. And this is a a vector with 125 positions that represent this first document here. Okay. So the idea here is that take each one of the documents that you have in our training data set, represent them as using this representation, and then fit a machine learning model to predict the class of this of the document. Okay, so we create this big matrix X that will contain the representation of every document in our data set. And then we can proceed with the same training steps that we did with the bag of words approach. So you'll see that I'm testing with three different values of the parameter C, three different type accuracies that I have. I fit with the whole data set, and then I test using the test documents. And you see now that the precision is not as good as it was with the bag of words, the bag of words approach. Okay. So this is the confusion matrix. Okay, let me see if it works. Okay, sorry. Just a second. And the accuracy score, you see that before in the previous exercise, it was 0.88. Now we have an accuracy of 0.76. Okay. Okay, so Word2Vec is very nice for presentation of words, for playing with semantics of words, not as good for text classification. Okay, so for text classification, if you want to use Word2Vec, you'll need something more. Okay. And there are other different types of approaches that use this representation also for, but we are not going to see them in this lesson. Okay. Let me see just if see if it works. My confusion matrix works. Okay. Okay. This is the confusion matrix. Okay. Questions?
No.
Okay, we still have 20 minutes, right?
Yeah, 10, 15 minutes at most.
10, okay, 10, 15 minutes. Okay, great. So let's go to the last exercise and the most advanced exercise, that is using transformers. We are not going to the details of the transformers because I cannot do it for sure in 20 minutes, in 15 minutes for sure. That's the idea here is just like to see how to check what is the representation of the documents in this approach and see what are the results. Okay. So in this case, I'm going to open in Colab because I will need the GPU for this. Okay. In the Colab, once you open the notebook, just on edit and notebook settings, be sure that you have GPU activated. Okay. Okay. And now let's run the cells of this notebook. First, it should install everything. And then this import here should work. Okay. Okay. This error is not a problem. We import again the same data set with the same 5,000 examples. And then the first part, the first step to prepare the data set to give into this type of models is the tokenization part. So the tokenization is how the how you divide, how you take your string and you divide in different pieces. Okay. So every different model. So we are going to use later. I'll just I'll just use a few minutes like to talk about this model that we are using. Is the Distilbert model. It's one of the most popular transformers that are used for text classification. It's one of the fastest ones also. Since we are using this model here, we need to use the same tokenizer that is being used, that was used for the original model. Okay, so the way that we create the tokenizer is just assign to a tokenizer variable this from the trained, and you see and you tell which model you want to load. Okay, which type of tokenizer you want to load. Okay, so it should download it for you. And then also in the tokenizer, you should have a vocabulary. So let's see what's the size of the vocabulary in the case of this tokenizer. You see that it's a vocabulary, it's quite small. It's like 30,000 tokens, okay? If you want to check, for example, what is the index of the token amazing? So the index of the word amazing is this number here, okay? And you have mostly for the more common words in a dictionary in English, you should have a token for that word, okay? For many words, you don't have a token for it, but we'll see in a minute how it works for the case of these words, okay? So let's load a sample. So let's see this the same example that we have seen, the same bad review that we have seen before. And let's apply the tokenizer to this example. And let's see what are the indices. So you see that this phrase, this review here was transformed in a list of indices. These are the indices of the tokens that the tokenizer recognized in this review here. Okay. So just to show you how the input is tokenized, you see that it starts always with a special character, is a CLS, and then for every word you have a token. For some of them, you see, for example, banal is not a very common word. But how you represent a word that is not in the dictionary? In the dictionary, you have a word that is banned, but you have also another, let's say, a piece of word that is all. If you join them, so you have the word banal, okay? You have for the other, for example, whomever, you have the same type of representation. So it splits the words that are not in the dictionary in words, pieces of words that are in the dictionary, okay? And this is the things that you see here in all the different parts where you have this sort of symbol here. So track list, in the dictionary you have track and you have list. So you can represent it as two different words that are in the dictionary, okay? Okay, so this is the way that the input, so the document is represented as a list of numbers. So now it's a list of indices, okay? This part here just apply the tokenization for every single document in the dataset. Okay. And you'll see that it will take just a few seconds. Another thing that is that this type of model, they are able to work with the inputs that are at fixed length. So, for example, this model that we are going to use here, you need to give as input a list of 512 tokens, always. So what happens if you have a document that has less than 512 tokens? The remaining positions are padded with zeros, okay? And if a document has more than that, then it's just truncated, okay? And this is the step that we are doing here. So for every single document, we just either we pad with zeros or we truncated them to 512 indices. And you can see here, for example, for the first 10 documents, if I try to represent them as, if I check what is the representation now, you see that it is a matrix with 10 rows and 512 columns, okay? And just see exactly show you exactly how this matrix looks like. Okay, and this is the input that you are going to give to the model. Okay. Okay. Now the nice thing about transformers is that you can download models that are pre-trained on huge data sets. So, for example, this Stilbert model was trained in a huge data set of many web pages that were downloaded from the web, documents from Wikipedia, and everything that you could download from the web, they used it to train this model, okay? So you already have a pre-trained representation of the words that you have in the dictionary that you saw above, okay? So the way that you do is you just call this auto model from pre-trained, and now what we are going to do is just download the model and the pre-trained weights that were trained on this huge data set, okay? So let's see what happens. So we can, right away, we can already use this model, okay? It's not trained in the task that we need now, but we can already use this model, okay? So if you take the sample that we have before and give as input to this model, you have an output, okay? And this output gives you a representation for each of the 106 words that you have in this input. You have a representation, a vector representation of 768 values, okay? So for this, on the top of this model, now we have to add layers for classification. The way that you do this is very simple. So you just ask, you just change from this auto model. You tell that you want to load the auto model for sequence classification, and now it's going to download again. No, it's just going to load, but now it's a model that is already prepared for classification. Okay. And now this part here, since I don't have much time, I just quickly tell you that these are the arguments of the training. So where the results are going to be, the learning rate, batch size, these are all parameters that are needed for the learning algorithm. And then you create a trainer object, giving as a parameter the model, the arguments that you set here, the training data set, the evaluation data set, the tokenizer that you created before, and also this data collator that is this part here that is just does the padding and truncation. Okay. And now you can run this cell here, and you'll see that if you run locally, it will take a very long time. But if you run on GitLab, it will take a few minutes. Okay. And okay. While it is training, maybe I can stop here and give you some time for questions. Just to complete the lesson, so you can save the model and then after download it and use it in another notebook for classifying other documents. And these are the other two notebooks that I have in the repository. They just one of them just downloads this model, loads this model and gives you the performance in the test data. And the other example is just an example of the same type of approach using transformers for a different task. It's just for text for translating from one language to a different language. Okay. While it's training, just a second, I'll just check if it's really training. Okay, now it's training.
André, my question here is, so then
yes.
Can you use then this to do the same classification of positive and negative reviews
yes.
as you tried so, but you haven't tried.
Yes, I'm training the model, and the last step that I'm doing here is saving it to somewhere. So I'm saving it to disk. And so the next notebook was really if I have just a few seconds just to show you how the test works. So in the test, you just load everything.
Okay.
And then you have you can apply for text classification, and you have another accuracy. So the accuracy in this case, I can tell you already using this data. This data set and the amount of data that we are using to train this model with parameters that I set is going to be around 0.89. Okay.
Yeah.
So
and
it's not. Yeah.
No, I just was thinking, what is the part where you feed the model to the classifier? So the model that you have saved is just the language model, right? And the classifier, how does it read the So
you need the data for the, let me see if I can, okay, here. You need the data for the training part. So
okay.
Yeah, so it's here. Yeah, here. Here's the data that you are using to train.
Yeah,
okay?
yeah, okay. Yeah, now I see it. Yeah.
Once you train it, then you can save it. You don't need the training data anymore.
Yeah, and just you go. You
just the model.
The test set. Yeah, okay.
Yeah. So in the other notebook, where is it? Here. So in this notebook, we use, if you look around here, you use just the test data, you see?
Yeah.
I'm not using the training data here, just the test data to measure the performance.
Okay. Yeah. Okay, so this improves with respect to the bag of words.
Yeah, the bag of words, not very impressive improvement, like a bag of words, if I remember well, was 0.88. But it depends on the amount of data that you use for training. Remember that I'm using just 5,000 samples. If you use the whole data set, if I remember well, this accuracy can go up to 0.93 or something like that.
Okay.
Okay. Questions? Sorry if we don't have much more time, but yeah, if you have any questions.
Any questions from the audience here or someone online? Feel free to ask. If not, well, then thanks, André. Thanks a lot for
Thank you.
For your presentation and for the code.
Okay, I hope that everything. I know that it was very fast. Mainly the last part that was the most advanced one. It will take a very long time to explain how transformers work, but it's. I think it was interesting to know at least that with just a few lines of code you can train a model. And also you can use it to classify things. In the other notebook, you'll see that it's very easy also to do translation with this sort of model. And if you have any questions, if you need anything, any help, just let me know and I'll be here to help you.
Okay, yeah, thanks so much, André. Yeah, no, it's, I mean, the last part is clearly more, yeah, I'm here just showing. It's clearly more advanced and also more complex, but I think it's been a good complement to the beginning of the lecture of today that also presented some of these language models, but in more from a theoretical point of view. So we could see them now a bit of application in code. And so thank you again, André, and see you soon. And well, this was the end of today's lectures. So we are gonna meet tomorrow again at 9.